strain curve of concrete compression is typically like this. It's not linear. There is an ascending part. There is a peak. The peak strength is called the ultimate strength. And if you have a good testing facility, you can also trace what is happening after the peak. Otherwise, it will suddenly fail. You need a stiff testing machine, or you need proper displacement control loading, way big now. It's only then you can capture the post-peak behavior in concrete. Concrete is a brittle material. Then you find that the curve descends, comes down. The first question to ask is, why does the slope continuously degrade? First question. Secondly, why does it come down after peak? Doesn't happen in steel. In steel you have, mild steel if you see, you have a strain hardening region and apparently it comes down, but that's not the true stress strain curve. Why? Why? Because that's the apparent stress strain curve, because you are dividing the actual tension with the original cross-sectional area that you calculate. Actually, the cross-sectional area reduces. There is necking, and so your strength doesn't ever come down. In concrete, it's not that. The strength comes down. Why does the strength come down? Of course, you can completely ignore that part of the behavior. That's a different matter altogether. But if you were to include it, why does the compressive strength reduce after hitting a peak? Which means it can still take some load, but not as much as it could take earlier. First of all, have you ever thought of this question, or you automatically know? If all these great people say the stress strain curve looks like this, it must be like that. Gospel truth, no question. That's not how we want to practice it. You must question everything, everybody, with humility. So why does it come down? Brittle material breaks suddenly. That's the meaning of brittleness. No warning. Glass.
The plastic deformation. Plastic deformation.
You have that in steel, but it doesn't come down. Well, the true answer is we really don't know. We say this behavior is called softening. Most big behavior is softening. A lot of micro cracking takes place inside the cylinder. And you know, in fracture mechanics, there's a fracture process zone, and then it breaks up. But it is also to do with the cement paste. You know, the heterogeneity of the mixture really comes alive. So there's a lot of extensive micro cracking before it actually breaks apart. So it's found to come down like this. And here I have a set of stress strain curves. The peak value. So on the y-axis we have plotted compressive stress. This is stress, and on the x-axis strain. Now, this would this axis that would be plotted. So this is like F50 concrete. You could be asked a question, sketch same scale the stress strain curves of M20 concrete and M50 concrete. So you must show this behavior. This is 50 MPa, this goes to 40, etc. This is about 50, 80. Is it clear? So from these set of typical stress strain curves of normal concrete, we have not gone beyond 50. What conclusions can you make? So this is a kind of training you should develop as an analyst. By looking at graphs, you should be able to make good inferences based only on the graphs. Peak value remains same. All right, that's an interesting observation. Apparently, more or less, the value at which the peak stress is hit, the strain is roughly around 0.01. That's a good observation. They all hit the peak roughly at the same time, and that's the reason why in our code they say in action compression, take strain as 0.1. Okay, good. First observation. Any other? First of all, be careful when you use words like Young's modulus. Young's modulus assumes linear, perfectly linear stress strain behavior law being followed. And for an elastic material. So we don't use the word Young's modulus. Just say elastic modulus, fully acknowledging that it's non-linear, we assume it will be fully linear in the initial region. So you're talking only about this region or you're talking So what's your question? Any answer? So first let's get the observations. You made one observation that all there seems to be a constant strain at which the ultimate strength is attained. What's the second observation before you ask the questions? First you must observe, then you must question. You jumped into the question without observation. What's your observation? As the grade of concrete increases, now you went to another observation. As the grade of concrete increases, the failure strain decreases. So can you put it another way? As the grade of concrete increases, material tends to become more brittle. Because the larger the failure strain, the greater the sign of ductility. Where you hit the peak and the strain that you get after peak, if you get that significant, in steel it's huge. In mild steel it's as high as 25-30%. This is a little bit, almost as much as this. By the way, these are all variable. If you repeat the test, you get a little variable. So that's your second observation. What's the third observation, which he hinted at? As the grade of concrete increases, the initial tangent modulus increases. Now how do you define modulus of elasticity of material with this kind of stress strain? Young's modulus. Will it be initial tangent modulus? How do you define it? So we'll hold that question, but you answer this. Now we'll go to this question. Why does it increase? Higher strength, you have higher elastic modulus. Why? In steel, it's not like that. Fe250, Fe415, Fe500, even pre-stressing steel, which can go up to 2000 MPa, more or less have the same elastic modulus, 10 raised to 5 megapascals. But in concrete, if the concrete is of low strength, the elastic modulus is also low.
It's not linear. Now, with more strength.
Even if it's linear, it increases with strength. See, every curve is not linear. So he's saying, whichever strain you take, whether you take the tangent modulus or the secant modulus, it's always higher when the grade is higher. That's the observation. It has nothing to do with nonlinear. Why? Why is the concrete stiffer when you have a higher grade? Well, clearly, it's also obvious from the correlation that you have. EC is equal to approximately 5,000 root FCK. So as FCK increases, EC also increases. Yes, so you should realize there are correlations between his observations. Correct. See, it sometimes takes an outsider, a mechanical engineer, to give the correct perspective. It's stiffer, so it looks like it's more solid. And if you more solid means the fluid part is less. So you know, normally if you want to make a richer mix, you have to cut down the water. Cut down the water cement ratio. It's a harsher mix. You'll automatically get an increase in strength. So that's the primary, intuitively, it's the primary reason is that you have less voids in the mix. The microstructure is more compact. And so the density is also slightly more, obviously, but not too much. The variations in density are not so significant as the variations in elastic modulus. Okay. So as strength increases, everything increases. Tensile strength also increases, density also increases, bond strength also increases, shear strength also increases, elastic modulus also increases. Good. So those are the three observations that you have. The higher the concrete grade, the steeper is the initial portion of the stress strain curve, the sharper the peak of the curve is the less the failure strain. In one sentence you can capture all this. For low strain concrete, the curve has a relatively flat top with a high failure strain. The descending branch of this stress strain curve, referred to as softening, can be fully traced only if the strain control application of the load is properly achieved. For this, the testing machine must be sufficiently resolved. Okay, let me ask you this question. We are doing tests on uniaxial compression, and ideally a cylinder should be used. That's why you draw the stress strain. You can't do it on a cube because you have a disturbed stress strain. But we use the same stress strain curve to deal with beams, flexural members. Is it justified? You remember when you do open capacity of a beam, you use the same stress strain curve. How to verify that it's the same? If you had to do an experiment, what would you do? How would you do it? In fact, probably you have to do it in your lab. People have done a lot of studies on this. So you can create small column-like systems where you can apply an eccentric load. So first you make it concentric, you got pure axial compression. Then you slowly shift it so that you have compression with bending, just like you have in a beam curve. And when you take the eccentricity very far, then you find that the axial compression part is less, part of the section can go into tension. And typically we use the word strain gradient. There is a strain gradient across the depth of the section. So you have uniform, then you have a strain gradient. Let me ask you another tricky question. Where is the neutral axis in a column section subject to pure axial compression? Huh? Centroid. Why is the neutral axis the same as the centroid axis? is the neutral axis the same as the centroidal axis? Why is the neutral axis? We've learned this, we're doing it mechanically, isn't it? Why is the neutral axis the same as the centroidal axis? One at a time. Yeah.
So when the central load stays between the middle third of the tension will not be.
Now let me confuse your thought. I have a beam. Span L. You're saying middle third meaning the middle and then. Is that what you mean? What do you mean? You have to answer. You have to clarify. The student gets totally confused. It meant something, but you use words like beam and you got into a fix. You understand? We find that all our learning is muddled like this. We picked up some rules, middle third rule, this rule, that rule. We really not understood. Can someone answer this question?
Load a cross section within the middle third, which means the eccentricity on either side can be maximum.
No, we'll take the same beam we talked about.
For the same thing, it's about the middle third of the cross section itself.
How do you do that? Tell me clearly.
You are loading and the axial load actually passes through the.
No, where is the axial load? I got a beam.
Yeah.
They usually put a load normal to the beam, no? Can I apply the middle
Then
third?
it will generate a moment. At a cross section, it will generate a moment, a transverse force. So transverse force being, we can break it down in the cross section as P by A plus M by Z. So once you
Where's the beam?
we
I
bring
got
the
a beam.
force.
I got a load in the middle third. Where's the beam?
Is the longitudinal axis of the beam. It is eccentric to the longitudinal axis.
I'm not able to understand this. He talked about beam. All our normal understanding of beam is they simply supported beam. You put a load here. You're saying don't put it in the middle, put it in the middle third. Okay, I'll put it in the middle third. Where the hell do I get a beam? I get a bending moment actually. I get a shear force. I don't have an actual force. What are you talking about? My eccentricity is 0. I have only bending moment. My eccentricity in that sense, if P is 0 is infinity. Thoroughly confused you all, right? That's the idea. And only you learn. Okay. This also will put on hold. Yeah, I'm raising questions. You guys have to reflect, discuss over a cup of tea. What do you do over a cup of tea? You have a cup of tea or not? What do you chat? You have politics. Huh? What? Well, once in a while you can discuss these questions. Very interesting. Okay. So we'll put that on hold again. Well, all I want to say is that it's been experimentally proved that when there's a strain gradient, you get more or less the same stress strain curve, but you'll find that you get a larger failure strain. This is experimentally proved. That's why in the IS code, in other codes, we have a failure strain which is as high as 0.0035 when you have bending. But in compression, we don't rely on the post-peak strain. We limit it to 0.01. But otherwise, we use the same stress strain. Got it? Experimental studies have also confirmed that the stress-strain relation for the compression zone of the reinforced concrete flexion member is nearly identical to that obtained for uniaxial member. For the purpose of design of reinforced concrete flexion members, various simplified stress-strain curves have been adopted by different codes. For low-strength concrete, the curve has a relatively flat top and a high failure strength. So that was for strength up to 50. If you go higher than 50, then the brittle behavior really shows up. Okay, so there's a tremendous drop in failure strength. Now you can write equations, you can fit curves. The easiest curve to fit is a parabola. At least up to the peak, it's a parabola, so you can easily write expressions for that. But for high strength concrete, we don't say it's necessarily a parabola. So there are many formulations. Don't worry too much about them. Okay? tell me. Is it good to have little extra beyond the peak? In engineering. See, you have a shirt with a button. One fine day the button vanishes. It's not good, no. But it gives you warning sign. First it will loosen up a bit. Then you know its thread is going to come out. Then you get. Have you done it? Have you saw it? So it's good to have little warning, no? That's the main purpose. Somebody said. Have little cushion so that you can take action. So ductility gives you warning. The failure is not sudden, the collapse is not sudden. You get some cushion. What happens in that cushion period? See, today for example, she's alone. There were 3 people supposed to do the video. Najib Sharif fell fallen sick, he got fever. The other person, Rohit, is sitting in the back. He came late, he had a bath, he even in pain, so he forgot. These things happen. When they happen suddenly in the crisis, critical moment, it's difficult. But you need to have redundancy in the system where you can, other people can handle it. Right? So she got Philip to fix this. So you get some time to react, to make up, to change. So definitely that cushion period for warning, for anything. Let's say you have a cyclone. When it comes, the super cyclone which hit Orissa didn't give enough warning. We didn't have technological data to. Today we can predict the coming of a cyclone, where landfall is likely to be. You can do preparatory measures. You can evacuate the region if required. So in life, it always helps to be forewarned. There's a saying in English, to be forewarned is to be forewarned is to be forearmed. You can arm yourself. Arming people should know. Right? Otherwise you have a sudden attack, you can't handle it. You have these jets scrambling to so always it happens, whether in tension or in compression or in life. Clear? Any more questions?
In uniaxial compressive strength, actually the failure happens by lateral tension. So are we not measuring tension indirectly?
Okay, I'll put his question in a different way. How does the cylinder fail? Visibly. What do you see happening? Clearly, I want people who have actually seen, describe to me what happens. Then I'll paraphrase this question. What happens when you load a cylinder and you slowly watch? How long does it take for it to break? You're guessing. Then people who actually done the test. You've done the test or not? You've done the test. How long did it take? A few years? A few minutes? Okay. Less than 5 minutes. Depends on the rate. Okay. Now the question is, did you observe clearly what's happening? What happens? Axial compression. You can't actually see it going down because it's too small. EA by L initially. You put some Dimec gauges, you have a compressor meter which can measure and all that. But visibly what do you see? You see cracks. Crack means what? Whenever you say crack anywhere, what does it mean? Flower vase is cracked. Wall is cracked. Release of energy, okay, but in terms of compression tension, what does it mean? Whenever you say a crack, what does it mean? Your crack opening, what? You have tension. digressing, but let's say this is a partition wall. And I have a long horizontal crack. What's your conclusion? Who's applying? No, like, I'm asking a very practical question. You've seen this in many places. The wall is high, 3.5 meters. I have a long horizontal crack. It's a masonry wall. You are engineers. What's the use of doing MTech in structural engineering? You can't ask this. See, it's so easy to read books, memorize standard answers and reproduce them. But when you deal with real life, it's so difficult. But real life is more important than all this remembering theory. What will you do? So MTech structural engineering from IIT Madras has visited the house. Come, let me show you. I have this crack. Tell me what to do. What will you do? What will you do? Sir, I have not finished my MTech. You don't have to give lectures on what. Actually, what you will do, physically, what you will do. A good engineer, a good doctor first will diagnose the problem. You are straight away wanting to hide the problem. You grout it again, it will rain. If it's a structural. What will you do? Shall I again leave it open and you will never be able to answer anything? What will you do?
Find the reason.
Find the reason. I am asking you what will you do to find the reason?
Maybe even settle. Wow. Not settled.
Huh?
Settlement due to you.
If you have settlement, usually you won't have horizontal. You have inclined, you have diagonal. That's the first thing. When will you get an X crack on a wall? I have a rectangular wall. I'm going completely off target, but I think this is important. Okay, I've got a wall like this. I get an X crack. Seismic, you know that, you've seen pictures of that. Why do you get an X crack in seismic? You have to explain why you get one crack in the first place.
There's a reversal of
Diagonal tension, diagonal compression.
Do that. Let's take one crack at a time. This crack, when will you get? Go on. Load bearing. Which load causes it? The gravity load will cause the crack? There's not partition wall, there's an actual load bearing wall, it's a shear wall. In a house, typical failure pattern you see the next crack. The ground is here, the ground is shaking, right? Why do you get this crack? Because that's why you have to use both parts of your brain. The left hemisphere is a logical, rational thing. Right one is the intuitive thing. Right one they say is feminine, whatever it is. Why will it crack like this? Whenever you say crack, you should know that there is tension normal to the crack. Something is pulling it that way. Who's pulling it that way? Then you go to deformation, you'll understand. So you have to use your right brain and tell me what's happening. I get a crack like this. Bottom is more or less fixed to the ground. What movement would have caused that crack? Will it be a movement this way or this way? A crack is like this.
So
This way?
This way. No.
Sure. Huh? Why?
Then we need to detect. In this direction, there is a shear.
You're right. So, one of the diagonals is elongating, the other is contracting. Right? So, this is the length of the diagonal here. Oh, sorry. And you know the tension is this direction. So, this diagonal when you move in this direction, would have elongated, the other would have shrunk. So you've got an extension. Masonry is brittle, tensile strength is low, it will crack. But the earthquake is a reverse cyclic loading, so it will move the other direction as well. That's why. Okay. With that background, tell me what you do with this. Arey yaar, don't get into solution because all your solutions won't work if you have not diagnosed correctly.
It's not vertical.
I'll tell you, I've actually seen these problems. I'll tell you what I did. And it was falling down. The moment I saw the crack, first of all I knew it was not a settlement crack. I asked the question, what could have caused it? First of all, it was a pretty wide crack. First I'm curious to know, is it a direct tension crack or is it a flexion crack? So how do I find out? If it's a direct tension crack, it's a crack through and through. If it's a flexural tension crack, the other side will be compression. So what should you do to find that out? What should you do to find that out? Arey yaar, take a walk. Go to the other side of the wall and see, and you'll see that there's no crack there. Engineers should learn to walk, not sit still rigidly with their stupid ideas and not be open. So immediately you know, you got an opening on one side, you got a closing on the other side. So what could have caused it? Then you look up and say, oh, now I know. What is it? Huh? Arey, where is the load? It's only self-standing. Yeah, you can see clearly that the wall is not vertical. It's out of plumb. Due to its own self-weight, it is, and especially partition walls which are thin. Flexural stiffness is low. Construction is very important. It should be plumb, vertical. Even a little off, that eccentricity can cause you action. That's where your P by A plus some minus F by Z comes in. It's a flexural tension capacity can crack, and obviously it's running right through. Next solution we won't discuss, but grouting is not the solution. Okay, have you understood? So everywhere we'll discuss more such practical problems so that you know. Right, why did we talk about all this?
Cylinder.
First thing you'll notice is vertical crack. Yes or no? None of you said that. You're saying tension, blah, blah, blah. You get cracked in the middle moving up and down, right? They're spread out. That's when you see, oh my God, it's bulging out. Right? But I'm applying an action compression load. How do I get a tension crack? That's his question. Am I right?
No, sir.
Wait, let me ask that question then. Where do you get a tension crack? I'm applying compression. How will I get tension? Huh? Poisson's effect, correct. What is Poisson's effect? Will I get a tensile stress? Will I get a tensile stress? Strain. So I have action compression, I am applying a load, I get action compression strain, I get a hoop tensile strain, and concrete is weak in tension, it will split in many places. What's your question?
By this cylinder test, are we not indirectly measuring the tensile strength?
Everything is correlated, yeah. Poisson's effect. The root cause, is it the lateral extension or the primary compression? Which is the root cause? This is an effect. This is the cause.
So is this called crushing? What is happening?
This is not crushing. This is called Poisson's effect. Tensile cracks appearing. But it doesn't fail, it can take more load. We'll see what happens to the Poisson effect when you look at it 3D. It takes more load, eventually it crushes. And it's a pretty explosive crushing if you do it in a step. So it's like, stay away, remove the compressor meter, stay away, make a sound. And that's crushing. Crushing means it becomes Part of it gets crushed to powder. Crushing.
That is the
Crushing
last
is not
point.
cracking. These words are both begin with CR and end with ING. Crushing is in compression, cracking is in tension. Got it? Sometimes both happen. But the early signs are cracking, vertical cracks, crushing is. Any more questions?
The crushing point we obtain by the final point in the stressing curve.
Yes, that's when it gets crushed. After it can't take any more load. Once the movements are so large, it can't take any more. Got it? Clear? Going very slow, but I think we need to clarify these basics. Okay. So you can write equations. Now let's say you unload the curve. And let's load it for some level and we unload it, it'll come like this. You load it again, come like that. Load it again, come like that. Load it. So this kind of quasi-static loading, many cycles of loading, you don't go below zero, you don't go to tension. It's interesting because for almost all materials you'll find that if you trace the peak points and draw an envelope curve, it's more or less the same as what you would have got had you done monotonic loading. Very interesting. Supposing I had loaded this and without reversing the load, then I would have got this. But if I load it, then unload it, then load it, then unload it, then load it, then unload it, the peak points will kind of trace the same. Very interesting thing. More or less.
There is no cyclic hardening taking place.
That means there's no hardening thing, you're able to recover to some extent, but still you can see from this graph itself, you're not dealing with an elastic material. Because in an elastic material, you don't have residual strains, you're getting residual strains. Concrete is not really an elastic material, that is, it does not fully recover its original dynamics. It is not only non-elastic, it is also non-linear. That is the stress strain curve story. Nevertheless, elastic constants are material properties that have to be necessarily considered in the conventional linear elastic and absolute reinforced concrete structure. That's the first thing you need if you want to solve an indeterminate problem.
Linear.
Good question. That's the next question. Okay. You can define the modulus of elastic many ways. Initial tangent, okay. Tangent modulus, secant modulus. Three definitions are common. Okay, so this is your curve. So there are three standard rules. One is you take the initial. Okay, when you unload it, it's not going to get the same one. Right, you're going to lose some. This initial line is for the initial tangent modulus. If you take some point here, say some specified stress, then you have two ways of doing it. You can take the local tangent there, or you can take the secant from the origin. This point is typically taken as the service stress level. Okay, we've exaggerated this nonlinearity here. Actually, it is more or less straight. I'm just to distinguish between these definitions, I deliberately made it more non-linear than it actually is. It's more or less straight. Now, this you can either specify a stress level or you can specify a strain level. And say roughly we don't exceed that under service loads. Okay, you know that non-linearity rarely happens when you have large. What is non-linearity? Did I discuss it? Your grandmother asks you, you're saying, I'm doing PhD in non-linear analysis, non-linear stochastic dynamic analysis. So she gets totally said one word at a time. Tell me what is non-linear. Grandmother in the village. Don't talk of concrete. Don't talk of Poisson's ratio and tension. Talk in a language she'll understand. What is non-linear? Okay. deposit the money, you dig a grave, dig a hole in the ground and deposit it there. After some time, it will vanish. Or after 10,000 years, in archaeological survey, they might discover it. You have to, a sentence is a sequence of words that make sense. Anybody? What is non-linear behavior? Typical non-linear behavior which you see even here. Yes, Nikita. Grandmother. Language she will understand. I'll give you a clue. She likes mangoes.
5 rupees costs for 1 mango.
Right?
2 mangoes.
5 rupees cost for 1 mango is bad English. If 1 mango costs 5 rupees, okay.
Then 2 won't cost rupees 10.
2 will cost 10 rupees, she knows.
No, it won't cost.
Your scales are very low. 1 mm deformation, 2 mm deformation are the same. You'll have linearity there. Grandmother, have you not bought mangoes from the market? She says, of course. So, which is the mango you like? You don't like mangoes, that's why you're not able to answer. Who likes mangoes here? Which mango do you like? Himsagar, huh? Okay. What's the cost of 1 Himsagar? 1 kilo. 1 is too small. 1 kilo. 15, 16 rupees.
No, not 50. 50, 60.
50, 60 rupees. Grandmother says yes. But she bargains very well. She gets it for 50 rupees. 2 mangoes, how much it will cost? 100 rupees. Grandmother, if you buy 10 mangoes, how much will it cost? How much will it cost? I want to know, no, I will get it for 450 rupees. She said. 1,000 kilos, how much will it cost? Then I'll get it for half the price. Grandmother, that is called non-linear behavior. You understand? You always get a discount. But you must buy sufficiently large. You must go to wholesale market and buy it, not retail market. Oh, that's what you're doing. I'm doing same thing. Instead of buying large mangoes, I'm looking at large movements of the structure. When the structure moves a lot, I also get similar discount. Right? The stress comes down, the initial period. Oh, why didn't you say that in the beginning? No big deal. Anybody can do it. Okay. So you will find that up to service loads, 1 kilo, 2 kilo, 3 kilo, 4 kilo. But large deformations, gone. You can't use the same thing. So usually this is taken at roughly 1/3 the ultimate strength of concrete. You're not supposed to cross that. You remember your old working stress method. Your allowable stress was roughly of that order. Factor of safety was 3 or 4. 3 in flexure, 4 in compression. Remember? So it's more or less straight then, right? Then you have a choice. You can choose this definition, you can choose this definition, you can choose. Which should you choose? Which has been chosen for you in 5,000 rule FCK? Secant. You're right. Why?
Among the three, it is like in between. Initial tangent is very high.
Initial tangent is very high, tangent is very low. This is kind of an average stress, it's average behavior over this range. So you may not hit this, you may be somewhere in between. Average behavior is similar, very similar. Okay. Now we'll look at horizontal. Now I'm drawing 3 kind of strains which will answer the question. See, this is stress, and I've normalized it by dividing by the cylinder strength, specified cylinder strength. On the x-axis, I have strain, micro strain, 10 raised to minus 3. This is compression, this is tension. So this blue line that you see is a typical standard stress strain curve in the longitudinal direction. Clear? Now I'm going to measure strain in the lateral direction. That means in this case I'll take the circumference and see the change in the circumference at the mid height of the cylinder. then I see its tension, it's bulging out, so it's taking a similar path. And the ratio of this strain to this strain, this strain, lateral to longitudinal, is called Poisson's ratio. Got it? But something happens after a certain, both become non-linear, and at some stage there's a dramatic increase in the circumference diameter. That's when crushing is initiated. Got it? We'll also look at what's happening to the volume change. So that's a volumetric strain. You find the volume initially becomes less until the bulging is so much that it switches from compression to tension. Broadly, this is the behavior. We can intuitively understand this. Clear? Next question. Let's look at duration of loading. Typically, a test you do is 5 to 10 minutes. If you do deformation control, you take your measurements. But let's say we do it more slowly. You've heard this concept of gradual loading? Structural analysis say gradually load. Why do they talk of gradual loading?
It's not sudden. It's not sudden.
How gradual is gradual?
Sudden is this stuff.
How gradual is gradual? That's where you get your stress strain curve half gradually loaded. No, you want to make it so gradual that it's a static loading. There are no inertial effects. There's no acceleration. So in your mind, you could load it for 1 million years. Who cares? It's only in your mind. Right? That's gradual. It's clear? So similarly, if you were to load, 10 minutes would be this, 1 hour would increase your peak stress slightly. 1 day is this, not increase, decrease. Okay? So if you do it faster, you get a higher strength. If you do it more slowly, you get a slightly lower strength. This is well known. If you take 1 year to load, you do that. That's intuitively obvious. In fact, if you had a heavy vehicle and you had to cross a bridge, what's a clever thing to do if you had a doubt? Go so fast that the bridge has no time to react. By the time the bridge thinks of what went through it, you reach the other side. If you go slowly, the bridge will sag, it might collapse. It's a small thing. Do things so fast that guys won't notice it. Same is true here. It's more the duration of loading. And this drop could be a little bit. In reality, loading is slow. We don't test to crushing in 5-10 minutes real life structures. We hope they don't even fail at all. They should last, you said, 50 years, 100 years. So then what is the value of, you realize the strength should not be taken as full F-C. You must give a discount here. We will see this in the next class.
0.025 strain.
0.002. Well, it flattens out, but our reference is always a cylinder test. So our reference is always 0.0. Okay, we'll make adjustments later. Time, this becomes flatter, that's all you can see. We'll stop for today.